Hello and welcome to Math with Mrs. Becker. Today in College Trig, we are going to look at the fourth and final part of section 4.1. We get to look at some applications of something that is called angular speed and linear speed. Now for me, this is really fun. So actually I brought home 3 sets of notes, and without even realizing it, I actually completed all of them. So as I go through the notes on this video, I'm just going to have to use a blank sheet of paper. I guess that's what happens when you are a true math nerd and you fill out all of the blank notes. But don't worry, we'll get this figured out. Okay, so when you have like a wheel or a tire or a fan or a merry-go-round, any of those things, when it rotates, there's actually 2 different speeds that are happening. So just like the last couple days as we've been talking about angles, you can measure your angles using 2 different things. You can measure them in degrees, and you can measure them in radians. So when something rotates, there's 2 different speeds. It's so cool. So the first one is called an angular speed, and it's how many times the object turns per unit of time. Now remember, every single time you make a full revolution, so you do a full circle, it is 2 pi radians. Your angular speed will be always measured in radians. Common labels that you will have would be radians over seconds or radians over minutes. Theta is the angle, again make sure that we are in radians, corresponding to the arc length, which is s. Then the angular speed, we use the lowercase Greek letter that is called omega. Now remember, trigonometry originated, and even the word is a Greek word. So that's why it's so common to see all of these Greek letters. So what we do to find angular speed, which we use that variable omega, it is our radians. So our angle measurement in radians divided by time. Okay, and it says, note, when we are figuring out angular speed, the size of the circle is insignificant. And no time when you're figuring out angular speed do you need to know the diameter or the radius. You just need to know how much of a rotation you had, so how many revolutions, based off of how much time. Let's just go ahead and do some. Okay, so here's the first example. I'm trying to not show you the answer already. All right, a saw makes 1,800 revolutions per minute. So that's RPM. It's revolutions per minute. What is the angular speed? In order to do this, you need 2 things. You need theta and you need time. Theta is how much of a rotation you made. So it's 1,800 revolutions. Every revolution is equivalent to 2 pi. Because remember, when you go full around the circle one time, that is 2 pi radians. We are going around, or this saw is going around 1,800 times. So it's 1,800 revolutions. Every revolution is 2 pi. So this is 3,600 pi radians. That's how much that thing traveled. In 1 minute, that's crazy. So our time is 1 minute. So our angular speed, the speed at which it rotates, is theta. So 3,600 pi radians per 1 minute. So you could leave it like that, or you could simply say 3,600 pi radians per minute, since it's a 1 on the bottom. And that, my friends, is angular speed. See why it was so fun? I had to do 3 sets of notes, just, because. Let's go ahead and look at the next one. So now we're looking at a Ferris wheel. Okay, so Ferris wheel, super fun. I'm sure everybody's been on a Ferris wheel. We can calculate angular speed. So when you're on a Ferris wheel, you guys, you're doing trigonometry. Super cool. Okay, so a Ferris wheel makes 3 revolutions in 2 minutes. To find the angular speed, you need to know 2 different things. You need to know theta. You need to know the angle in radians. That is based off of the number of revolutions. We're making 3 revolutions. Every revolution is 2 pi. 3 times 2 pi is 6 pi radians. So that is your angle. Okay. Now, how much you can do those 3 revolutions in what amount of time? It's 2 minutes. So my omega, which is your angular speed, how fast is the Ferris wheel rotating around in a circle? It is theta, so 6 pi radians over your time, 2 minutes. I can reduce 6 over 2 to make it 3 pi, and it's radians per minute. That is the angular speed, the speed at which the Ferris wheel rotates in a circle. Let's do another one. Okay, the second hand of a clock takes 60 seconds to make 1 full rotation or revolution. What is its angular speed in radians per second? So again, in order to calculate angular speed, you need to know theta and you need to know time. So the second hand of a clock takes 60 seconds. So that's what the time is. It's 60 seconds to make 1 full revolution. So it goes around 1 time. When you make a full revolution, that is equivalent to 2 pi radians. Your angular speed, the speed at which the second hand rotates around the circle, is 2 pi radians. It's theta over time, 60 seconds. I can go ahead and reduce. 2 over 60 would be 1 over 30. So it's pi over 30 radians per second. And that's what they were asking for. What is the speed? You want the label radians per second. And it's important to look at that because as we move forward in this section, we are going to be doing quite a few conversions. We'll be going from inches to feet and feet to miles and minutes to hours and all those really fun things, which is why I think this section is kind of awesome. So your solution here, look, that's what I got earlier when I practiced. It's pi over 30 radians per second. Okay, so remember I said that there's actually 2 speeds. The first speed is called angular speed because you're focusing on going around the circle. Linear speed is if you focus on 1 point on that wheel, okay? You're not looking at the whole thing and as it travels, you're focused on that 1 point. You want to know how fast is it going? Like how many feet is it moving in a second? Or how many meters in an inch? Or how many miles in an hour? Okay, or another way, maybe if it helps you to visualize, what if I put that wheel on the ground? Okay, so like if you're picturing a Ferris wheel, rather than having it just going around and around, what if I put it on the ground and it actually traveled forward? So it was like linear speed. You want to know how fast is that sucker traveling? If you put it on Highway 10, what is its mile per hour? Okay, so that's what linear speed is. When you are calculating linear speed, we use V. Okay, V is the variable that is often used to represent linear speed. The formula, it is R. Remember, R always represents the radius in trigonometry. So R, you take the radius times omega. So you have to find your angular speed. You take your angular speed and then go ahead and multiply it by whatever the radius of the circle is. So it's really cool because you already know how to find angular speed. Once you have that, multiply it by the radius and bam, now you have your second speed, which is called linear speed. So fun. Okay, so here is an example. The second hand of a clock is 8.6 centimeters long. So if you picture a clock, okay, if we're looking at the second hand, that would be a radius, you guys, because it starts at the middle and then it goes around. So the radius is 8.6 centimeters. Find the linear speed, they want it in centimeters per second, of the tip of the second hand as it passes around the clock face. So we want it in seconds. So the time that it takes for the second hand to go all the way around, that takes 60 seconds. Our angle, we're saying, okay, it's going to make 1 full revolution. Every revolution is equivalent to 2 pi. So it's traveling 2 pi radians. Now this is what I like. In order to calculate your linear speed, start off by finding your angular speed. So you're going to be like amazing rock stars at calculating angular speed because we already practiced that. And now that's step 1 to finding your linear speed. So our angular speed, you do not need the radius for. It is just theta over time. 2 pi radians over 60 seconds. And yes, this should look a little bit familiar. We just did this problem. 2 over 60 reduces, so it's pi radians over 30 seconds. That's your angular speed. Now to find your linear speed. What is the actual speed that it's going? Like we're looking at in 1 second, or how many centimeters does it travel per second? Okay, so we're looking at the speed. You take the radius. So 8.6, the label is centimeters. You rotate it by our angular speed. Now, one thing that happens when you do this, the radian label is eliminated, but the bottom seconds will stay. So this is going to be centimeters per second. When you do this, it's top times top. So I have 8.6 pi, the label is centimeters, over 30 seconds. Okay, now, yeah, this is a really cool answer. But when you're talking about linear speed, you always want to know what the actual speed is. So what I mean here is we got to calculate it, okay? Angular speed, perfect, because it's in radians, and we were graphing angles in radians, so we can kind of visualize that. Linear speed, you're not going to say, hey, I was driving down Highway 10 going 8.6 pi divided by 30 centimeters per second. Like, everybody's going to look at you like you're crazy. So when it's a linear speed, go ahead and calculate it. 8.6 pi, that's the top. Now divide that by 30, and it's going 0.9 centimeters per second. That is your linear speed. Okay, so again, angular speed, leave it in terms of pi. When you calculate that linear speed, though, you really want to go ahead and calculate that out. Okay, let's look at another one. Oh, a merry-go-round. Okay, merry-go-rounds are super fun, so this is going to be a great problem. A merry-go-round makes one full revolution every 10 seconds, okay? So we have theta, one revolution is 2 pi radians, so we have 2 pi radians because of my one revolution. It happens every 10 seconds, so there's your time. Time is 10 seconds. Yeah. Okay, cool. So at this point, you guys, because the radius doesn't matter, as long as I know those two things, I can already jump ahead and find my angular speed. What is the speed that the merry-go-round rotates? So omega equals theta, 2 pi radians over 10 seconds. I can reduce. 2 over 10 is the same as 1 over 5. So this is pi radians over 5 seconds. That's its angular speed. So every 5 seconds, you're traveling pi radians. And when you picture this, remember when we were graphing in standard position? This is 0, this is pi over 2, this is pi, this is 3 pi over 2, and this is 2 pi. Every 5 seconds, it goes to pi. So 5 seconds, 10 seconds. Oh, yeah, 5. So we got 5 seconds, it'd be here. 10 seconds, it would be here. 15, 20. So knowing that pi is half a circle, every 5 seconds, it makes it halfway around the circle. So as a visual, it's really cool. That's why we graph these things first. So as we're doing these problems, you kind of have a reference as to what the heck I'm talking about when I get really, really excited, and I've done the notes many times. Okay, let's keep on going. So we have our angular speed. Now, linear speed is just the radius times the angular speed. So let's go ahead. What is the linear speed in miles per hour of a kid who sits 2 feet from the center? So here's the center of the merry-go-round. This kid is sitting 2 feet from the center. So when we're looking, we're focused on this circle right here. So guess what? 2 feet is our radius. So the radius is 2 feet. So I have to go ahead and take 2 feet times pi. Remember, when you multiply, the radians is going to be eliminated, and it's 5 seconds. So this is going to be feet per second. Top times top is 2 pi. It's feet, 5 seconds. I can't reduce it. So what this means is every 5 seconds, it's traveling 2 pi feet. But that's not what the direction asked. The direction said in miles per hour. I hope you like your conversions. So we start with 2 pi feet per 5 seconds. We need to convert it to miles per hour. Okay, I really like taking care of the time piece first. So what that means is I want to go ahead and make seconds into hours. So I know that 60 seconds is equivalent to 1 minute. And remember from doing, when you're doing these conversions, you want to be able to cross cancel. So seconds is on the bottom here. That's why I need it on the top so I can cross cancel. So right now I have it in feet per minute, but I want it miles per hour. So I need to convert minutes to hour. Minutes is on the bottom, so I need to have minutes on the top. 60 minutes is 1 hour. Now I have minutes cancels minutes. So if I look at my labels, right now I have feet per hour. They want miles per hour, so I need to cancel feet. There are 5,280 feet in 1 mile. Feet cancels feet. So what I have now is miles per hour. When you are calculating this, top times top times top, leave pi in it till the very end, because otherwise you end up with decimals and it kind of gets a little funky. 2 pi times 60 times 60 times 1. Whoa, whoa, whoa. Leave the pi. I just told you to do it and then I didn't. 2 times 60 times 60 times 1. It's 7,200 pi. The label on the top that has not been crossed off is miles. On the bottom, it's 5 times 1 times 1 times 5,280. So the bottom is 26,400. The label on the bottom that was not crossed off was hours. Now again, this is our linear speed. You're not going to say, hey, guess what? That merry-go-round was going 7,200 pi over 26,400 miles per hour. Okay, that doesn't mean anything unless you actually calculate it out. So we want to go ahead and go to the decimal. So it's 7,200 pi, there's the top. Now divided by 26,400, that thing is going slow. So we have approximately 0.86 miles per hour. Okay, so let's say that kid who was sitting, so we're going to keep going. Let's say that kid was sitting 2 feet from the center. Well, this was kind of slow, right? And that kid's like, I want to go a little bit faster. So they're wondering if I go to the outside, if I go further from the center, will I speed up? And so what happens is they move, then they're 5 feet from the center. So I got to go back here. The radius is now 5 feet. So it's 5 feet times our angular speed, which is pi radians per 5 seconds. Whoa, this cross cancels this. Remember, the radians is not there anymore, so we are looking at just pi feet per second. Well, we want it in miles per hour, otherwise it really doesn't mean anything and we can't compare it. So if I have pi feet per second times seconds, there are 60 seconds in 1 minute. Seconds cancel seconds. There are 60 minutes in 1 hour. Minutes cancel minutes. Okay, so I have hours. Now I need feet. There are 5,280 feet in 1 mile. Feet cancels feet. My label is miles per hour. We're ready to go. Don't multiply the pi in until the end. So if I take 60 times 60 times 1, I have 3,600. I still have the pi. Label on the top is miles. On the bottom, 1 times 1 times 1 times 5,280. The label that I did not cross off on the bottom is hours. So by that child moving, they were 2 feet from the center. Now all of a sudden they're going 5 feet from the center because they want to see if they can go faster. Let's see if it worked. 3,600 pi divided by 5,280. Whoa, look at that. Now that's a daredevil. They're going 2.14 miles per hour on that merry-go-round. I hope you guys are having a good time. This stuff, I really do like it because it's showing you how trig really applies to real life. When you are pushing a kid on a merry-go-round, you're doing trig. And if that kid wants to go faster, they need to sit further from the center. The closer you get to the center, the slower you're going to be going. That's really good to know if you ever go to a park and you start getting motion sickness. Okay, real life stuff. Let's go ahead and look at the back. Oh, look I think I tried. Oh, that's my ceiling fan. This is why I don't teach art class. All right, let's go ahead. More examples of angular and linear speed. So we have a ceiling fan. That's my ceiling fan. Okay. We have a ceiling fan where if you look, we have 16-inch blades. So that's what this is. So that's my radius. So the radius is 16 inches. I'm sure I didn't mean for anybody to see that, but that's what you get when you fill out all the notes. Okay, it rotates at 45 rotations per minute. That's what RPM is, rotation per minute. So theta is 45 rotations. Every rotation is 2 pi. 45 times 2 pi, that's 90 pi radians. How long did it take? That's your time. That's rotations per minute. So you guys, that's crazy. That is 1 minute. That fan whipped around 45 times. Holy smokes. It doesn't look that great, but that's a good fan. Let's go ahead and figure out the angular speed, and they want it in radians per minute. So omega is theta 90 pi radians over 1 minute. Okay, radians per minute, that's what they want. So this is 90 pi radians per minute. That's your angular speed and we're good to go. Okay, now let's keep going. Find the linear speed in inches per minute. So linear speed, you have to take the radius. Oh, this is beautiful. It's in inches, so it's 16 inches times 90 pi. Don't worry about the radians. The bottom label will hold though. It's minutes. So if I go ahead and take 16 times 90, this is 1440 pi. The label on the top is inches over minutes. Now again, this is our linear speed. You want to go ahead and calculate it. So 1440 pi, there's the numerator. If I'm dividing it by 1, it's not going to change. So we have 4,523.89 inches per minute. So that's ceiling fan every single minute. If there was like a speck of dust or maybe a ladybug on there. So if there was a ladybug and you're just looking at that one spot, the actual speed that it's traveling, it would go 4,523.89 inches every 1 minute. I hope that ladybug took Dramamine, because that's kind of fast when you're thinking about it. Let's keep on going because I'm having a good time and I hope you are too. Hey, look at this. I get really excited every time I go ahead and move this. I'm like, okay, I hope I got the same answers. All right, let's go ahead and go on to shop class. We have a radial saw and it has a blade with a 6-inch radius. Radius equals 6 inches. And it rotates 1,000 revolutions per minute. Holy smokes. So we have our theta. It is rotating 1,000 revolutions. Every revolution means that it's actually traveling 2 pi. So we have 2,000 pi radians as our measurement for theta. And this is revolutions per minute. So that means my time is 1 minute. So if I want to find the angular speed in radians per minute, angular speed, there's omega, it is theta, 2,000 pi radians per 1 minute. So it's 2,000 pi radians per minute. That's what they wanted, radians per minute. What is the linear speed? Linear speed, we have to take it times r. So it's 6 inches times 2,000 pi. It will no longer be radians, but the minutes on the bottom will hold. So if I take 6 times 2,000 pi, I get 12,000 pi. It's inches per minute. Now let's go ahead and see what they want, okay? They want the linear speed of the saw teeth in feet per seconds. We have inches per minute. So we're going to go ahead over here so we have some room to do some conversions. So 12,000 pi, it's inches per minute. If I want to go to seconds, I need to cross cancel minutes. So I know in 1 minute, there are 60 seconds. Minute cancels minute. So right now I have inches per second. They want feet per second. So I need to cancel inches. inches is on the top, so I need inches on the bottom. 12 inches goes in 1 foot. Inches cancels inches. So now I have feet per second. I can go ahead and multiply it. The top is 12,000 pi. The label is feet. Over the bottom, if I take 60 times 12, I get 720. The label on the bottom is seconds. They want it in feet per seconds, okay? When you're doing this, this is our linear speed, so we go ahead and we calculate it in decimal form. 12,000 pi, there's the top, divided by 720, so our linear speed is 52.36 feet per second. That saw blade, so the teeth on the saw, every second, they travel 52.36 feet. That's pretty intense. Cool stuff, cool stuff. Okay, I want to make sure I got the same thing. Yep, 50, oh, good, good, good. Okay, now we're going to go ahead and look at the wheels of a car. Not like the wheels on the bus, but we're going to look at the wheels of a car. The wheels of the car have a radius of 11 inches. So radius equals 11 inches. They are rotating at 600 rotations per minute. So theta, it's going 600 rotations. Every rotation is 2 pi. So if I go ahead and take 600 times 2 pi, I have 1200 pi radians. That is theta. That happens at 600 rotations per minute. So my time is 1 minute. So if I want my angular speed, it is theta, 1200 pi radians over 1 minute. So again, I can just simply say 1200 pi radians per minute. Okay, so we have that. Find the speed of the car in miles per hour. So I need the linear speed. Okay, our angular speed is always radians per some unit of time. If we're looking at miles or feet or inches, we have to go to linear speed. Okay, and that's what I put right there. So linear, 11 inches times 1200 pi, the bottom label holds. So if I take 11 times 1200, this is 13,200 pi. The top is inches over 1 minute. Now before I go ahead and calculate this, I want to make sure it's in miles per hour. So you start here. Don't do pi until the very end, because as soon as you have pi, remember it's an irrational number. So you have crazy long decimals, and you don't want to deal with decimals till the very end, okay? So I have currently 13,200 pi inches over 1 minute. I want miles per hour. So I'm going to convert my time first. Right now I have minutes. I want it in hours. There are 60 minutes in 1 hour. Minutes cancels minutes. So now I have inches per hour. Well, I need miles. So I need to first go from inches to feet. There are 12 inches in 1 foot. Inches cancels inches. Now I can say there's 5,280 feet in 1 mile. Feet cancels feet. So now I have miles per hour. Top times top times top times top. Again, do not calculate in the pi. So 13,200 times 60 times 1 times 1. 792,000 pi. The label on the top is miles. Over 1 times 12 times 5,280 is 63,360. The label on the bottom is hours. Now go ahead and calculate. 792,000 pi. There's the top. Divided by 63,360. That car is going approximately 39.27 miles per hour. Now think of this. If you have a car where the radius of the tire is 11 inches, your car, the tires have to rotate full revolution 600 times in 1 minute to get you to go 39.27 miles per hour. It's kind of amazing. So now think of how fast you drive your car. Think of how many times that tire has to spin around and around to get you at that speed. This is some really, really cool stuff. Okay, let's keep on going. I think I cut a couple, maybe not. Oh, no, I did not. Okay, a Ferris wheel with a 50-foot radius makes 1.5 revolutions per minute. Okay, so again, a Ferris wheel, 50-foot radius. So radius is 50 feet. Revolutions, that helps us find theta. It makes 1.5 revolutions. Every revolution is 2 pi. So 1.5 times 2 pi is 3 pi radians. That happens every minute. So your time is 1 minute. So if I go ahead and I figure out the angular speed, omega equals theta, 3 pi radians over 1 minute. So it's 3 pi radians per minute. Got it. Okay, so find the angular speed of the Ferris wheel, radians per minute. Check. Find the linear speed of the Ferris wheel. Now, if it doesn't tell you, like it doesn't say feet per second, miles per hour, you get to just keep it at whatever the labels are. So for us, it's going to be feet per minute. So if I have linear speed, the radius is 50 feet, multiply it by the angular speed, which is 3 pi, the bottom label stays. 50 times 3 would be 150 pi. The label on the top is feet, over the label on the bottom is minutes. Now we are done. This is our final answer, so I go ahead and calculate it. 150 pi. If I divide it by 1, it would still remain the same thing. 471.24 feet per minute. Okay, I'm kind of looking at the time on this video. I want to make sure that I do cover everything, but I don't want you to get so bored that you stop watching because the best question is at the very end. So I think we're doing pretty darn good. Let's go ahead. We have to do the washing machine question, okay? So let's jump down to the bottom. It says a front load washing machine has a wash tub whose diameter is 20 inches. So remember from geometry, if the diameter is 20, the radius is 10. Okay, so if the diameter is 20, the radius is half of that. While it is in spin cycle, the tub makes 1,200 revolutions per minute. So you guys, when your washing machine actually does that spin cycle to try to get the water out of all of the clothes, that sucker goes around 1,200 times every single minute. So here's how we can get theta. It's 1,200 revolutions. Every revolution is equivalent to 2 pi. So this thing is going 2,400 pi radians. And it does that in a time of 1 minute. That sock is on like the ride of its life, let me tell you. Okay, so a front load washing machine has a wash tub. The diameter is 20 inches, so we have the radius is 10. It's in spin cycle. When that happens, the tub goes 1,200 revolutions per minute. What is the speed of a sock that is stuck to the outer wall of the wash tub while it's in spin cycle? So again, you have to find your angular speed first. So it's theta, 2,400 pi. It's radians per time per minute. That is the angular speed. So that's the rotation that it's spinning around the circle. We want to know the linear speed. I want you to know the miles per hour. These are real numbers. How fast is your sock going? Okay, so V, your linear speed, it's 10 inches times 2,400 pi. The bottom holds, so it's minutes. So this is now 24,000. I'm just adding a 0 because I multiplied by 10. Pi, it's inches per minute. Okay, so inches per minute would be kind of cool, but I want you to realize how fast it's going in miles per hour. So I know it's kind of a pain. We got to do another conversion, but let's go to miles per hour on this. 24,000 pi inches is where I'm at now, and it's at 1 minute. I want to go miles per hour. So let's convert minutes to hour. So 60 minutes goes with 1 hour. Minutes cancels minutes. Inches. 12 inches goes with 1 foot. Inches cancels inches. 5,280 feet goes with 1 mile. So now, where's my feet? There we go. Feet cancels feet. So let's go ahead. Don't calculate in the pi yet. So just take 24,000 times 60 times 1 times 1. 1440000 pi. The label on the top is miles. On the bottom, 1 times 1 times 12 times 5,280. It's 63,360. The label on the bottom is hours. So we have miles per hour. Ready to see how fast your sock actually goes while it's in spin cycle? You're not even going to believe this. 1440000 pi. There's the top. Divided by 63360. Yes, you are reading that right. A sock that is stuck to the side of the washing machine on spin cycle travels approximately 71.4 miles per hour. If that sock was on Highway 10, it could get pulled over and get a speeding ticket. This is why I love math, you guys. Like, look how fun this is. Now, again, I apologize. The notes, I know the video got a little bit long. We skipped a couple questions. However, when you look back at the beginning, we really focused on this angular speed. When we got down to linear speed, you did have to find the angular speed every time. We did conversions, making sure that you know how to go from inches to feet and miles and whatnot. And so I know we kind of stopped after this one. We skipped 2, okay? So let's say that you get to your worksheet today and you get stuck. Remember, you can always reach out and I can help you further. But I figured 36 minutes was probably a long enough video. I hope you enjoyed our time together today, and I'll check with you later.